You are muted.
Yes, I know. Sorry.
Okay.
Okay, I'm ready.
All right, start recording.
Hello, judges. My name is Antonia Kolb, and my project focuses on a viable and scalable application of photocatalysis for environmental remediation. So what does this mean? Photocatalysis is a chemical reaction that is driven by a light source, either by an artificial one or the sun. Two significant environmental problems are methane emissions and oil spills, the former invisible, so to speak, the latter one very much so visible. A vast majority of energy use is still from fossil fuels and carbon-based energy extraction, specifically of oil and natural gas, and these must deal with methane release and oil spills as natural byproducts or accidental consequences. Now, the environmental toll for not having effective contaminant and mitigation solutions is severe. Oil fields produce large quantities of excess oil that they cannot store or transport in an economical way, so they must burn it. While the while the intentional burning of methane is effective, it is also a significant loss of opportunity to derive energy from methane. While the unintentional spilling of oil is enormously expensive to contain and clean up at scale. Photocatalysis can be used for the safe and controlled degradation of both methane and oil. Methane is a potent greenhouse gas and is the primary component of natural gas, but it also has a global warming potential 86 times greater than carbon dioxide over a 20-year period, and therefore contributes to the Earth's warming we all experience today. Methane is a symmetrical molecule, and therefore the four carbon-hydrogen bonds are difficult to break, and after one is broken, it results in total oxidation into carbon dioxide. Using a novel photoreactor design and a cheap artificial light source, I aim to break only one of the bonds in total of methane to convert it into methanol, a viable source of energy, hence the term partial methane oxidation. However, currently direct methane oxidation and conversion to high energy density fuels have not yet been attained on a commercial scale. Current methods of both partial and full methane oxidation are unscalable, expensive, and energy intensive. This project aims to better optimize full methane oxidation to better achieve partial methane oxidation of methane to methanol, a viable source of energy. The COMSOL multiphysics modeling software was used to project optimal parameters for methane capture using laminar and turbulent airflow for both a real-world scale model and a lab-scale reactor model. The real-world reactor would have 1-meter panels with a maximum projected methane conversion of 5.4%. A lab-scale model would have 100-millimeter panels with a projected maximum methane conversion of 14.3%. This reactor would be placed in cow fields, oil fields, and other large sources of methane. The reactor was then built using LED lights as opposed to xenon lamps, which are typically used in photocatalysis, allowing the reactor to adequately scale in the real world due to its efficiency and affordability. Cadmium sulfide and gallium phosphide panels were then coated and functionalized with co-catalyst palladium silver titanium manganese oxide, as seen in the panel coating schematic here, and they were then tested in the photoreactor. Here was the mass spectroscopy data from the photoreactor from the experiments. The maximum methane conversion of both cadmium sulfide and gallium phosphide panels was around 2% methane conversion, with an increase in carbon dioxide concentrations in blue and methane conversion in red simultaneously, with reaction before and after the light was turned off, evidence of photocatalysis. Similarly, for the breakdown of oil via oxidation, I created a scalable photocatalytic process by formulating a ferromagnetic nanoparticle powder that can be placed on an oil spill for cleanup. Now, 1.7 million tons of oil are spilled into bodies of water worldwide, with companies spending billions on cleanup efforts in methods such as skimming and in situ burning, which are often cost prohibitive due to the large scale of oil spills. Now, superparamagnetic iron oxide nanoparticles, such as magnetite or Fe3O4, are known to have low cytotoxicity and excellent biocompatibility, displaying a promising application in oil spill removal. Due to the photocatalysis and proof of concept seen in methane conversion, I decided to explore the viable application in oil photodegradation for oil spill removal. I used an incipient wetness reaction to dope and co-functionalize these magnetite nanoparticles onto the copper oxide nanosheets, as seen here. And the two main goals of this experiment was to make the powder paramagnetic and hydrophobic. Now, using the incipient wetness reaction, I was able to deposit the Fe3O4 or magnetite and deionized water dropwise onto the copper oxide nanosheets until it turned to a liquid consistency. Now, this allowed for the powder to be magnetic due to the ferromagnetic properties of iron oxide nanoparticles. I then heated the previous powder with endodecyl phosphonic acid and dibenzyl ether to make the powder hydrophobic. The scanning electron microscopy, or SEM data, showed correct pre-reaction morphology, seen here in the component analysis. This was the SEM imaging of the magnetite pre-reaction, and this was the copper oxide pre-reaction. After the reaction, the morphology of the compound displayed the presence of copper, indicating that a reaction had occurred. Now, before the solvothermal reaction with dibenzyl ether and endodecyl phosphonic acid, which made the powder hydrophobic, the powder reacted well to the magnet. This was notable because the copper oxide, as seen before, pre-reaction was not hydrophobic nor ferromagnetic. Here it was tested in deionized water and hexane, and the nanosheets fell to the bottom of the vial as expected and did not react to the magnet when placed in a mixture of both hexane and deionized water. Therefore, I used endodecyl phosphonic acid and dibenzyl ether as protective coatings to make the copper oxide nanosheets hydrophobic, and the magnetite nanoparticles allowed for the powder to become magnetic. The magnetite and copper oxide powder from the incipient wetness reaction and the solvothermal reaction displayed both hydrophobic and paramagnetic properties. First, I placed a few particles of the magnetite and the copper oxide into deionized water. The powder remained above the surface of water, demonstrating its hydrophobicity, and it also reacted to the magnet seen here. Then, the powder was tested in hexane and deionized water solution. Hexane was tested because it is a compound that can be found in spilled oil and therefore was used to simulate an oil spill. The powder remained in the top layer of hexane and did not float down to the bottom layer of water. It once again, as expected, displayed magnetic properties and was drawn to the magnet. Here is a video displaying these ferromagnetic and hydrophobic properties. So, this demonstrated an applicable use in oil spills for both oil photodegradation and an embedded system of magnetic removal. This system was designed to be eco-friendly and highly scalable, similar to the methane oxidation reactor. Post-separation, the photocatalytic properties of the copper oxide will allow the oil to break down into non-toxic components that will not harm the environment in the presence of sunlight. The magnetic core from the iron oxide will allow for facile post-reaction collection and cleanup removal. So, in other words, these particles can be placed on an oil spill, they will cling to the oil, and afterwards the oil-soaked particles can break down the oil and the rest can be removed with a magnet. Here are two pivotal proof of concepts that can be improved upon. The lab scale model is currently converting 2% of methane, and with further co-catalyst optimization can reach the COMSIL model prediction of 14.3%, which would be capable in the real world of removing 100 kilograms of dilute methane from the air per day. The powder used for the oil photodegradation can also be scaled up and further tested. In summary, photocatalysis is a feasible method for breaking down key environmental pollutants, such as methane and oil. However, current applications of photocatalysis are neither viable nor scalable. But my novel applications of this method have shown to have both real-world applicability and are energy efficient enough to economically mitigate methane emissions as well as effectively remove oil spillage. I would like to thank Dr. Shu Hu and Jake Henline at Yale University and Dr. Victoria Schulman at King's School. Thank you, and here are my references.